Hi class, welcome to Refrigeration and Air Conditioning Lecture number 9, Isentropic Processes and Ideal Refrigeration Cycles. So in the last lecture, we learned about entropy, both from a classical thermodynamics point of view and also from a statistical thermodynamics point of view. Now we are going to look at some actual isentropic processes and how they are used for defining some ideal um, cycles, both heat engine cycles and refrigeration cycles in this lecture. So what exactly do we mean by an isentropic process? Um, Basically, there is no change in entropy, right? So basically, entropy by definition means uh, change in heat over a particular temperature in a process that is reversible, right? In this case, if it is isentropic, there is no change in heat, there is no heat transfer. So you could say that Q equal to zero, it's adiabatic. And there is no generation of entropy. So if there is no Q equal to zero um, and there is no generation of entropy inside or outside the system, you could say it's a reversible process too. So if it's adiabatic and reversible, then you can say it's an isentropic process. So in such a process, the only energy interaction possible is isentropic work. Okay, you've learned about work changing the energy levels of the particles within a system, but not changing the distribution of the particles within different energy levels. So that's what we mean here. If a work is done in such a way that um, it is not creating additional entropy. It is done in a reversible way, infinitesimally slowly, making sure that at each step all the particles are in equilibrium. Then such work is an isentropic work. And that's the only interaction with energy. That's the only energy change that could happen in an isentropic process. So such transfers are of course frictionless. There is no transfer of heat or matter. Okay. Isentropic processes are commonly associated with isentropic compression and isentropic expansion. So if you look at all the some examples of idealized thermodynamic cycles here, you can see several different types of cycles used in various machines. You can see the isentropic processes are either compression or expansion. Okay, those are the only two possibilities. So now let's consider isentropic processes, basically compression and expansion for ideal gas. We'll try to derive the relationship between temperature, pressure, and volume when a gas is either isentropically compressed or expanded, and especially when that gas is an ideal gas. So let's start with the first um, first law of thermodynamics, which is basically the energy consumption, energy conservation principle, which is this. And for an isentropic process, there is no heat transfer or heat, so dq is zero. So we basically get any change in internal energy is related to the work done on the system. Now, for an ideal gas, uh, in an isentropic process, the work done is basically the pressure volume work, and it could be represented by PdV. So du is minus PdV. And in the previous lectures, we have derived that the change in internal energy is only dependent on temperature, and the relationship is this for ideal gases. So rewriting that, we get the equation to be Cv dt is minus PdV. Further, using the ideal gas law, you can rewrite the pressure in terms of temperature and volume. So you finally get equations on both sides with respect to temperature and volume. Rearranging that and substituting for CV with gamma, which is basically the specific heat ratio, eventually you get the equation that TV to the power of gamma minus 1 is constant. Okay, and you could further substitute the relationship between PV and RT uh, to get the relationship between pressure and volume. And the volume here is basically specific volume and temperature and pressure. Okay, so these are basically the isentropic relationships between pressure, temperature, and specific volume for an ideal gas. So this is a summary of what we just derived. So pressure volume, the relationship is PV to the power of gamma is constants. Temperature volume TV to the power of gamma minus 1 is constant. And pressure temperature is this particular relationship, um, which is basically T to the power of gamma, P to the power of 1 minus gamma is constant. Okay. And gamma is the adiabatic index ratio of specific heats for which is basically CP over CV. Now you could calculate. Uh, so if you're assuming that an ideal gas went from one state to another, okay, and let's say this is a P versus T diagram. So it went from P1 T1 to P2 T2. Okay, we could estimate. If you know the P1, T1, and P2, you can estimate T2 using this equation. You could also assume, or you could also calculate P2 and, sorry, T2 if you know that this is an isentropic process. And if you have P1, T1, you calculate S1, the entropy here, right? And S1 is same as S2. S1 is equal to S2 because it's isentropic, right? So if you know S2 and if you know T2, you can calculate P2 using coolprop. Okay, so we'll basically try to calculate the properties both using this method and using coolprop and assuming isentropic process. Okay, so open your Excel file that says isentropic relations, and you could start with the gas helium. Okay, so you could see there are two sets of calculations, calculated using coolprop isentropic relations and calculated using ideal gas isentropic relations. And you could change the gas name here and it will change the properties that are calculated here. Okay, so you're varying the temperature and you're varying the pressure. You're calculating the pressure by assuming isentropic relation. So for the initial temperature and pressure, you calculate the entropy. For the next temperature, the corresponding pressure is calculated based on the same entropy. So you're using this entropy as the input. So using that entropy, and for the new temperature, what will be the new pressure? Okay, so these are all, so basically what that means, all of these will have the same entropy. Okay, so um, if I drag this down, first I need to, if I drag this down, you could see all of them have the same entropy, every row. Okay, so that's how we are calculating using coolprop. Now let's do the same thing here, but use the relationship of, you know, this particular relationship to calculate the second pressure. So you calculate the first, chosen the first pressure and calculate the second pressure using the isentropic relationships. And you have used gamma here, two temperatures, and one of the pressures to calculate the second one. Okay, so and so on. All right, and then basically what we're doing is we are plotting this pressure and comparing them. So you can see that both the pressures, if you look at this data, so it's plotting the pressure calculated using first method, and here it's calculating using second method. They're right on top of each other. The blue line and the orange line are right on top of each other. Almost no difference. Same way you could plot pressure versus specific volume. Okay, so you can do the comparison here. Um, the blue line and the orange line are right on top of each other. So for helium, helium is behaving like an ideal gas, and both these methods are giving it almost the same values. For neon, same. Like you can see that both the lines are right on top of each other. Same for argon. But when you start looking at air, you can see some differences, um, especially at certain temperatures and pressures, very high pressures. There is some difference in the values calculated using cool prop versus the ideal gas isentropic relations. So basically, what that tells you is at some conditions, air is not fully behaving like an ideal gas. Um, if you also look at nitrogen, which is a gas present in air, it's somewhat similar to air too. It does have some deviations, just like air was showing here. Okay. Now oxygen, it seems like this has more deviation than both nitrogen and air. Um, so this is a way for you to another way to for you to check the ideal gas behavior and at what conditions it tends to be more of an ideal gas versus less. Okay. All right. Now let's look at ideal refrigeration cycles. There are typically three of them that are considered ideal. The most ideal one is, of course, the Carnot refrigeration cycle. It's applicable to any fluid. Of course, all these ideal cycles are theoretical. It's impossible to reach these ideal cases, and Carnot is the most impossible one. Um, so when we're talking about impossible ones, any fluids could be considered here because it's not practical anyway. So it's applicable to any fluid. The processes involved in the cycle fall into two categories, isothermal and isentropic. Okay, so you could see isentropic is present in all of them, right? And that's one of the reasons they are ideal processes, because there's nothing called isentropic in real world. So isothermal and isentropic, it provides the most highest efficiency of all refrigeration cycles, not practical, and it's mainly for theoretical benchmarking. Brayton refrigeration cycle, um, again, not practical fully, but you could say that systems tend to get closer to this, um, especially because the isobaric portion is again, there are pressure losses, but you could say you could get close to isobaric process, and you could get a pseudo isentropic compression and expansion using turbines and compressors. This is only for gas. There is no evaporation or phase change in this system. Okay, so it is again not 100% practical, but you could say that it's used for modeling the refrigeration systems for aircraft cooling and for cryogenics, where you liquefy gases. So liquid nitrogen and liquid oxygen, things like that, where you want to get extremely low temperatures, then they use a combination of Brayton refrigeration cycle and Joule-Thomson expansion to get there. So ideal vapor compression cycle. This is the one where the domestic and industrial refrigeration systems are mostly modeled on. It has basically three types of processes inside: isobaric heat rejection and addition, and there's isentropic compression and isenthalpic expansion, which is like Joule-Thomson. Um, the efficiency is usually higher than the Brayton cycle, but lower than the Carnot. Okay, it's widely used. Again, when I say it's widely used, it's the non-ideal versions of these that are widely used. Okay, there are no non-ideal versions of Carnot that's possible. At least there are some non-ideal versions of Brayton and um, vapor compression cycles possible. To analyze these systems, let's first start with a Carnot heat engine. So if you remember this, we had discussed that the the efficiency of Carnot heat engine is basically um, 1 minus QL divided by QH, right? Which is also equal to 1 minus TL by TH. Okay. Um, and how does this relationship happen in um, so this is for any heat engine, and this is for Carnot. Okay, so Carnot is basically a reversible heat engine, the most efficient. So the process, you could say delta S equal to 0. So let's try to derive this from this. Okay, so if delta S is 0, delta S that's happening at the high temperature source, delta S here is you're losing heat, so it's minus Q minus QH, and you're losing heat at temperature TH, right? So delta H there is minus QH by TH. Delta S here, S1, delta S2, is you're gaining heat here on the sink, and you're um, gaining heat at temperature TL. So the delta S is QL by TL, it's positive. And this is um, reversible work done because it's the best possible system. So that means S gen is 0. So the total delta S is basically minus QH over TH plus QL over TL plus S gen, which is entropy generated outside, is 0. The total is 0. And this is 0 anyway. So this gives us that QH over TH is same as QL over TL. So this basically means um, QL over QH is TL over TH in this scenario for Carnot. So this is how we get this equation, right? The other thing to note here is, maybe I haven't mentioned this in the last class. So delta S equal to 0 for reversible processes or isentropic. Delta S could be greater than or equal to 0, or delta S greater than 0 for irreversible processes, right? Delta S less than 0 is not possible for the whole system plus surroundings. So what does that mean? You cannot have a system where um, you only have QH or TH and everything is converted to work. So if you had a system where there is no Q losses, right, then your total delta S total will be minus QH over TH and will be less than 0, right? Not possible. Such a system is not possible because you cannot destroy entropy. That is the second law, um, basics of second law. So you have to have some amount of heat loss. So this is why 100% work, 100% heat cannot be converted to work. Okay, when heat is converted or transferred and converted to work, entropy destruction happens. You need to create some entropy somewhere else. Okay, so that it's never less than 0. And somewhere else, that entropy that you create, if that exactly matches the amount of entropy you destroy here, then you get the Carnot cycle. That's the most efficient cycle you possible. Typically, what will happen is you'll generate a lot more entropy here. So you'll have much higher QL at TL. So you'll have a lot higher QL at TL such that the delta S is greater than zero. It's not equal to zero. Okay, which is what happens in most work producing engines, which we have discussed in the last lecture. Most of the engines appear to have efficiencies under 45%. There are some combined power plants that touch close to 60%, but typically 35 to 45%. And for motorcycle engines, car engines, and all IC engines, maybe 20 to 30%. Okay, so 100% is not possible, and at whatever is possible at a certain particular temperature of the high temperature source and certain particular temperature of the low temperature sink, the best possible efficiency is given by this equation. So this is a heat engine. Now let's actually consider a cyclic device based on the Carnot cycle. So here we are just looking at the cycle as a black box. Now here we'll look inside that black box and see what's happening to the fluid and actually calculate the um, work done and energy transferred and derive at the same um, equations that we arrived here. Okay, so consider this, and the reason we are doing this is even though we know the answers for a Carnot cycle directly based on the entropy relationships, you will learn this method of analyzing a system, and it will be helpful for you to later analyze real cycles. Okay, not the ideal cycles like Carnot, where already the answer is known because of the ideal processes. You'll get experience in analyzing cycles and analyzing real cycles with the losses. All right, so here we have four states. The first state is state 3, and it goes to state 4 through isothermal compression. And then you have isentropic compression, isothermal expansion, and isentropic expansion to get back to the original state. Okay, that is on a pressure volume um, diagram. This is how it will be plotted on a temperature entropy diagram. So 3 to 4 is isothermal, temperature is constant, so T3 is T4. 4 to 1 is isentropic compression, okay? Entropy is constant, S1. T1 to 2, 1 to 2 is basically, again, isothermal expansion. Entropy increases too. And 2 to 3, again, entropy is remaining the same. So 1 to 2 is isothermal expansion, 1 to 2. Then it's basically going up, and expansion means volume is increasing. So basically, during this time, there is no energy transferred. There is energy transferred Q in, and during this time, adiabatic expansion, there is no energy transferred. You could also say isentropic expansion. Okay. Isentropic is basically adiabatic plus reversible. So it's happening really slowly and it's reversible. There's no friction. Okay. And then it comes back. Initially, it's isothermal compression. So you're exchanging heat. And after a certain point, it's doing isentropic compression. So there are only two times that it's exchanging heat during this process and this process, during the isothermal processes. During the isentropic process, there is no Q. All right. So how do we estimate the overall energy transfers during the whole cycle? First, we look at the work done. Okay, so work done is typically calculated based on the type of process it is. So we know the work done formula for isothermal and isentropic from the previous lecture. If you don't remember, it's again derived here, okay, for isentropic and for isothermal. So 1, 2 is isothermal and 3, 4 is isothermal. So both those works done is derived here in terms of the volumes and the temperatures. Okay. Same for isentropic. Um, we have 2, 3 and 1, 4 or 4, 1. So both those work done values are calculated here. Now, the total work done is sum of all these works, and it turns out to be this value. Okay. You could also write it in terms of in this value by changing V4 over V3 to V3 over V4. Okay. So we know the net work done. Okay. This is the net work done in a cycle. That is nothing but this W that is coming out, W net. Okay. W net per cycle. Okay. So now what about um, the QH and QL per cycle? Now let's determine that. Um, so work done is basically QH minus QL. And sorry, I skipped one slide. So for process 1, 2, if you do an energy conservation, um, only we're talking about the only process 1, 2 where there is a heat transfer. So if you do an energy conservation for that process, it's QH equal delta U plus W12. Delta U is 0 since it's isothermal. Okay, because du for isothermal is CV dt. Okay, and dt is 0, so du is 0. So there's delta U is 0 for that scenario, so QH is W12. And we already know how to calculate W12. We have calculated in the previous slide. Similarly for QL, it is W34, and we know how to calculate that. Okay. And if you compare W, the value of W net we already got here, and look at um, the values for QH and QL, we realize that W is nothing but QH minus QL. Okay. All right. So now we have W is QH minus QL. Now the efficiency is basically output or input, right? So output is basically work, and the input is basically the amount of heat that's being put on the inlet side, how much heat you're putting. QL is the waste, okay? So in other words, you could write QH minus QL over QH, right? So you substitute all these numbers in there, you will end up getting 1 minus TL over TH, okay? So, okay, so this equation basically comes back to this. So we have derived this using actual work done calculations, actual heat transfer, and we have derived this equation in a different way. Okay. So far we have been looking at heat engine, Carnot heat engine cycle. So the input to the system is basically high temperature heat source, and we are basically generating work output. Okay, so it could be a turbine that is providing the work output. But in reality, in refrigeration cycle, what we need is we need to make some particular region cold by removing heat. So you actually want to pull heat from a low temperature space, and put that heat into high temperature region. So if you consider your room, you want to cool your room in summer. So this is your room in summer, and you want your room to be at, let's say, 23 degrees C, or 21 degrees C, and you want to put that heat outside your house, which could be at 39 degrees C, right? So you want heat to go from this way and this way instead of this, okay? So the refrigeration cycle is the opposite. And for this to happen, you need some work to be put in. And what the work that you're doing is basically um, primarily in the compressor of your refrigeration system. So you're putting in work to move the heat this way. So it's essentially the reverse of this. So if you look at every arrow here, every arrow is reversed. So this arrow is reversed in this direction, this arrow is reversed in this direction, and this arrow is also reversed. If everything is in reversed, it's a reverse Carnot cycle, okay, reverse Carnot cycle, and it's feasible, right? It's thermodynamically feasible, even though in reality it's not feasible 100% because uh, of the isentropic processes. So it's the reverse of Carnot heat engine cycle and converts work or uses work to transfer heat from cold reservoir to a hot reservoir. Okay, so it's basically this and this are coming out together on the outside. Okay, so if we look at the energy balance, it's QL plus W, okay, is giving us QH. All right, and you could redraw all the arrows and get the cycle for refrigeration on the right side here. So this is the heat engine and this is the refrigeration cycle. All right. Now, what is the efficiency of such a cycle? In this case, what is the input? So basically, efficiency is output over input. In our case, the input, what we are providing to the system, is not heat, it's work through compression primarily. So you could say W is the input. What is the output? Output is the amount of cooling that you're providing to your room or your refrigerator. So QL is the output. Okay. QH is the heat that is going to the outside or wherever we are sending the hot waste heat. QL is the useful input, or sorry, useful output that we are looking from the system, looking for from the system. So QL over W is the efficiency, and the efficiency is typically denoted by COP, coefficient of performance. Okay, so whenever it's a refrigeration cycle, we don't call it efficiency, we call it COP. You will also hear EER later on, but I'm not discussing right now. It's same as COP, but it's in a different units. Okay, so think of COP whenever you're discussing efficiency of a cooling system. And the reason for that is COP for most refrigeration systems are usually greater than 1. So normally when we think of efficiency, efficiency is usually um, less than 1% or 100%, but COP of refrigeration systems are usually greater than 1. The reason for that is QH is always greater than QL plus W. Um, so you're going to remove um, more heat um, from the system than the amount of work that you are doing typically. For some systems, COPs are lower than 1. There could be thermoelectric systems, for example, where the COPs are lower than 1. But for most systems, COPs are greater than 1. All right. So the next refrigeration cycle, other than the Carnot refrigeration cycle, is the Brayton refrigeration cycle. It's also known as reverse Brayton cycle, um, Bell-Coleman cycle. Sometimes it's also called the Joule cycle. Anyway, so these cycles are primarily used for aircraft cooling, cryogenics, and liquefaction. The main difference between this cycle and the Carnot cycle is that the heat rejection is happening isobarically. Okay, it's not no isothermal. It's isobaric heat rejection and isobaric heat absorption. The compression and expansion are all isentropic. So um, the cycles look slightly different. Okay, so how does the isentropic expansion and compression happen? There are turbines for expansion, okay, and there are compressors for compression. And you have seen that isenthalpic expansion happens during the Joule-Thomson expansion. So the isentropic expansion is much better than the isenthalpic. So if you are able to put a turbine instead of just a throttling device, you'll get much lower temperatures for such a gas refrigeration system. So if there was no turbine and you're having instead of S equal to constant from 3 to 4, you get H equal to constant and isenthalpic expansion, then the efficiency will be much lower. All right. When we use Brayton refrigeration cycle in aircraft, it becomes an open cycle primarily because um, in the cabinet or in the cabin of the aircraft, um, there is no the air is basically exposed to the chamber, right? So it's not contained inside a tube. It's basically the cold air that comes from the turbine is mixed with a little bit of warm air and spread to the cabin, okay? And some of it is exhausted outside of the plane, okay? And then some of them are recirculated, and then some of the air that comes in is coming from the compressor of the engine, aircraft engine, okay? Bleed air from the aircraft engine. And that goes to a secondary, this is a secondary compressor, okay? This is not the compressor on the engine. This is another secondary compressor attached to a turbine. So you don't have a fully closed cycle. It's partially open, okay? So which is why I've shown it to be partially open. But essentially, it's the same Brayton refrigeration cycle that's used in aircraft. And in the next lecture, I will show you some of the components used in an actual aircraft. All right, so how do we calculate the efficiency or COP of a Brayton refrigeration cycle? So just like we did that for the Carnot cycle, we will have to calculate the net work done and the energy transfer during the energy transfer processes, which are process 1, 4, and 2, 3 here. So the net work uh, done is basically the isentropic compression and the isentropic expansion. You could write that down in terms of um, the enthalpies, for example, and the net energy transferred during the high temperature process, which is T2 to T3, could be written like this, and the low temperature process could be written like this, okay? Um, and overall, the energy ratio, or the basically the efficiency ratio known as COP, could be written based on the QL, which is the output, and W net, okay? So overall, you could get an equation like this as a ratio of temperatures. You can rewrite them in terms of pressure ratios, where P2, the two pressures, okay, there are only two pressures in the system, P2 and P1, high and low. Um, So if you take the high pressure and the low pressure stages, and you take that ratio to be gamma P or RP, you can rewrite in terms of that also. So overall, you could write the efficiency of the Brayton cycle in terms of pressure ratios and gamma, or you could write in terms of temperatures if you know the temperatures of at least 3 stages or 2 stages. Okay. All right. So how does it compare to Carnot refrigeration? If you look at uh, this particular chart here, the rectangular region is the Carnot cycle. So Carnot cycle has isothermal heat transfer and Brayton cycle has isobaric. So it turns out that this is a more efficient process than the isobaric heat transfer process. So the efficiency comparisons based on the temperatures that are shown here, for Carnot it will be based on T1 and T3, the high temperature and the low temperature. T4 and T1 are the same, T4 prime and T1 are same, T2 prime and T3 are the same. Okay, so Carnot is this. For COP Brayton, it is based on this temperature. Okay, this temperature. So this ratio is typically smaller. This tends to become this if 4 tends to become 1, right? So if 4 and 1 get closer, if the cycles become thinner and thinner, okay, if it's really thin, then the Carnot cycle is almost same as the Brayton cycle. So if T1 approaches T4, and there's not a lot of temperature change between 4 and 1, then it is getting closer and closer to a Carnot cycle. All right. So we have discussed the Brayton, we have discussed the Carnot refrigeration cycle. The third one basically is the vapor compression cycle. So in this case, there is isentropic compression. Isentropic compression only happens in one of the processes. Okay, isentropic process only happens here. Uh, the expansion process is basically isenthalpic. Okay, and you can see this is the first time we started using pressure enthalpy diagram. Um, the heat rejection and addition process are isobaric. Okay, constant pressure, constant pressure. So there are three types of processes: isobaric, isentropic, and isenthalpic. Okay, isenthalpic. So this is the Joule-Thomson type expansion. Okay, where you're keeping the enthalpy constant and then expanding. Um, you could also see that we are inside the dome. For most of the processes, except compression. Okay, so wet compression is not possible. Okay, wet compression damages the compressor. Um, so it's always done outside the dome in the gas region. Okay, you don't go inside for compression. So you make sure that whatever liquid is coming to a compressor turns into gas and then does the compression process. And in reality, this cycle is not accurate primarily because isentropic compression can never happen. Typically, compressors have friction. Compressors run really fast, so it's not really slow. It's not in equilibrium. So isentropic compression doesn't happen. Okay, so now that we have looked at all these cycles, let's do some calculations in Excel. So open up the ideal cycles Excel file Go to the COP Brayton versus Carnot. Over here, I've selected several different T1, T2, T3, T4, and given you a comparison of the efficiency in terms of COP for both Carnot cycle and Brayton. And you can see uh, Carnot and Brayton cycles are um, have different efficiencies. Typically, Carnot has much higher efficiency. If the T1 tends towards T4, so if I reduce the difference between T1 and T4, then their efficiency will get closer. So you could see at that point, the efficiencies are getting closer. So um, when T1 and T4 are close enough, then the efficiencies match because Brayton cycle tries to mimic the Carnot cycle. Let's look at Carnot refrigeration on its own. We know the formula is this COPC TL TH minus TL. So what does that mean? So if you keep the low temperature constant, then the efficiency decreases as the high temperature increases. Okay, so this is somewhat opposite of the heat engine effect. In heat engine, higher temperature was on the higher temperature was a good thing on the high temperature source. Here, higher temperature or the highest temperature on the rejection side is actually a bad thing. So you want the TH to be on the lower side for better efficiency. And the place where you're removing heat, so let's say if you're removing heat from a room at 40 degrees C versus 20 degrees C, you will be more efficient when you're removing at 40 degrees C compared to at a lower temperature. Okay, so higher the temperature of the cold place from where you're removing it, the better the efficiency. Okay, all right. Now let's look at some actual Carnot cycle calculations here. So here you can see the charts for the Carnot cycles, the PV and the TS charts, and we have created that same ones using the actual numbers in here. So you can play with the numbers in these orange cells and change the locations of each state point. Okay, so when you do that, you will actually change the calculations done here for COP. I've done the calculations in three different ways. First one using the ideal gas formula. Okay, so the work done for ideal gases. So we know the QH, QL values calculated using the ideal gas formula, and then W calculated using QH minus QL and COP calculating that way. The other option was assuming isentropic properties in CoolProp. Um, we basically used entropy values calculated in QProp and calculated the QH using this formula, QL using this formula, and W using the same formula here. So you get an answer 5.263 here. Then we use the temperature formula, the well-known temperature formula for COP, and we got 5.263. So this was air, the fluid is air, so there is some discrepancy in the ideal gas calculated value versus the actual COP values. If we try a different fluid, for example, helium, let's say, so then these values are really close. All the values look really close because helium is more of an ideal gas than air. Okay, now let's look at Brayton cycle. Um, so Brayton cycle again, this is how the cycle looks from textbooks. So we tried to create that ourselves using um, the Excel file here. So there are four states are calculated, the P, T, S, H, all of those charts are in here, and the PV diagram too. Um, and again, we calculate COP using different methods. We calculated using enthalpy method, where QH, QL, and W are calculated based on the enthalpy. We also calculated based on the um, um, RP and gamma values, which I've shown you in the Excel file here. Sorry, in the PowerPoint file here, the RP and the gamma value equation. And we also calculated using the temperature equation here. All right. And then we calculated using the another temperature equation, T4 and T3 and T4. Um, and we also calculated the COP of Carnot and compared the efficiency of this system with the Carnot. So you could see that this is the most accurate. 2.722 is the value we are expecting. Um, so all the other methods are giving you some error because there's some assumption about ideal gas. So you want to actually calculate enthalpy at each state and then use that for the energy balance and calculating the work done. Um, the error in each method, the reason for that is given here. Um, and you can also see the COP is much lower compared to what a Carnot cycle would have had under the same conditions. All right, so that brings us to the end of this lecture. In the next lecture, we'll look at some of the applications of gas cycle refrigeration. And in the lecture after that, we'll look at the vapor compression refrigeration cycle. All right, thank you.